To parse top-down, a compiler makes a choice. Looking at a single piece of incoming text, like this A, it instantly decides which branch to expand. It can't back up. It must know the exact path forward, blind to the remaining code. That strict predictability defines LL1. The first L means scanning left to right. The second L means always expanding the leftmost non-terminal node first. And the 1 means the parser looks at exactly one lookahead symbol at a time. Because its vision is constrained, the parser cannot process ambiguity. The grammar must be perfectly organized so a single symbol provides all necessary instructions. This introduces the first mathematical condition. Look at these alternative production rules. Calculating their first sets shows exactly which terminal symbols they start with. To choose correctly, these sets must never share a symbol. Their intersection must be 0. If even one terminal appears in both first sets, the parser would have to guess. That immediately disqualifies the grammar from being LL1. The math holds up cleanly until a production can derive epsilon, an empty string. Here, we have a rule that produces A, and a rule that vanishes into epsilon. Their first sets contain A and epsilon. They don't overlap, so the logic initially seems fine. But imagine the input text runs out, and the parser reads the end of file symbol. It looks at the current rule, sees no $sign, and freezes. It doesn't know if it should report a syntax set of the non-terminal. It looks past the current rule to see what symbols are legally allowed to come next. Since the $sign is in the follow set, the parser safely chooses epsilon. This establishes condition 2. If a rule can derive epsilon, its first set and its follow set must have absolutely 0 overlap. We map these two mathematical conditions directly into a predictive parsing table. This grid uses non-terminals for the rows and the terminal symbols, plus the end of file marker, for the columns. Let's apply the math. If the rule A produces epsilon, and its follow set contains B and the $sign, where does the epsilon production belong in the table? Because it's an epsilon rule, we ignore the first set. The production goes directly into the columns defined by the follow set, under B and under the $sign. But if we feed the table a grammar where two rules start with the same terminal, both productions map to the exact same cell. A single cell holding multiple instructions breaks the system. The parser loses its strict one-choice guarantee, and the compilation fails. This parsing table is the final destination in a strict compiler pipeline. First, you write the grammar. Then you strip out left recursion, apply left factoring, calculate your first and follow sets, and build the LL1 table so the predictive parser can execute. To consolidate the mechanics, LL1 operates by scanning left to right, computing a leftmost derivation, and relying on precisely one lookahead symbol. The math demands that alternative first sets never overlap, and if epsilon is involved, the first and follow sets must also remain completely distinct. In your table, multiple entries mean your grammar failed the test and is not LL1. But if the parser hits an empty cell during execution, that simply means there is a syntax error in the source code. LL1 parsing forces ambiguous, human-readable grammar into a rigid deterministic structure. When the math aligns, the machine knows exactly what to do.